All right, everybody. Welcome to chapter 6, thermochemistry. So we're going to amp up the math a little bit in this chapter. You kind of have to for thermochemistry, but we'll take it as easy as possible, make sure we're explaining our steps as best we can, but we'll just jump right in. So the nature of energy. So you really think of energy, just as it says, the capacity to do work or produce heat. Heat is a form of energy, and conservation of energy says energy can't be created or destroyed. I was going to say lost, but it can be lost from systems, and we'll talk about that. But energy can be converted into different forms. So it's like a place where it can be lost is imagine a system where you're moving an object, and that object creates heat from friction. Well, then the heat will radiate out of the system, and at the end, if you calculated the final energy of the system, you would have less than the energy you started with. But that's because energy was lost when heat escaped the system. It's not that energy was destroyed or ceased to exist, it just changed into heat and left. But energy can only be transformed from one form into another. Different types of energy we want to really wrap our minds around are potential and kinetic energy. Kinetic, of course, is the energy of motion. Potential energy. So this is really energy stored in a system. So, the figure here is a good example of gravitational potential energy. So you have objects that are sitting way up high. Uh, the higher up they sit in a gravitational field, the more potential energy they have. Because if you think then if they started to fall or roll downhill, the higher up they are, the faster they're going by the time they hit the bottom. So they have more kinetic energy. So the higher up they are, the more energy they have stored, the more potential energy. In chemical systems, energy can be stored in chemical bonds. When you're working with electricity and magnetism, electric point charges, their fields produce a potential. And for electric fields, it's if you imagine another point charge or charged particle coming into that field, then it'll either experience a force of attraction if the charges are opposite, or a force of repulsion if the charges are the same. But that point charge has the potential to then act on that other point charge that could enter its field. For example, another example is imagine you have 2 point charges, say they're both positive, and you force them real close together. Well, the two positive charges don't want to be real close together. So the closer you push them, the more potential energy they have, because when you let them go, the harder they're going to push each other away. So that's the idea of potential energy. It's stored energy in a system. You remember we have a couple of equations here for kinetic energy that we were dealing with. We have the standard um, mechanics potential energy, which is 1/2 mass times velocity squared. The potential energy of a single particle in terms of temperature is 3/2 kBT, where kB is the Boltzmann constant. Or you have a mole of particles, where you have 3/2 Na kBT, where Na is Avogadro's number. And you remember that Na times kB is R. So for a mole of particles, your kinetic energy is 3/2 RT. We were working with that last chapter. Okay. So energy is the capacity to do work. So work is an idea in physics. It's a force applied across a distance. And so we'll see that a little bit. So work and force, and this is really we won't go too deep. We're not going to do vectors in general chemistry. You'll do it when you come to physics, but you just kind of want to get the idea. So it's going to be a operation called a dot product, but basically it's force times distance. And you're going to get, not equals, but you're going to get units of joules from work. So joule is the energy unit. So, for example, we just talked about this. Here's a system where work is being done on an object. It's force applied to move across a system. However, you also have this same work creating heat through friction. Um, in fact, the force that's creating the heat is the frictional force, not the force moving the object. So you imagine that there's a force as the object moves this way. There's a force pulling back this way, trying to stop the object. That's the friction. That force multiplied by the distance is going to create your heat energy that's created. So it's still a force over distance. In thermodynamics, we have these things called state functions. And we have to start thinking of quantities as dependent on pathway and independent of pathway. So, for example, heat and work are dependent upon pathway, which means the work done isn't just dependent on initial, like a final number minus initial number. So your delta. Work done depends on how you got from initial to final. So the path required. Heat is also it depends on how you got from your initial to your final value. State functions, however, don't depend on pathway. State functions are only dependent on the final and the initial and the final values. And so, here you see state A and state B. Well, it doesn't matter which pathway you go around. So you could choose path one or path two, doesn't matter. The, uh, the, uh, the state function, the value it's describing, is only dependent on the final state or state B and the initial state, state A, and it's a delta, final minus initial. Um, a thermodynamic equation you'll pick up as we go is you see delta H there, that's enthalpy. Enthalpy is so delta H equals delta U plus P delta V. Delta U we're going to work with here in a few minutes. That's thermal energy. And then P is pressure, delta V is change in volume. But this is the enthalpy of a system. Enthalpy is a state function. It does not care about how you got from the initial to the final enthalpy. It just cares about what the initial and final values are. So then this brings us to chemical energy. So, kind of a mock-up of an endothermic reaction here. We have to start understanding things. So, in thermodynamics, you want to understand what the universe is. And I know that sounds kind of like a Neil deGrasse Tyson, Carl Sagan kind of, let's talk about the universe. No, no, no. In thermodynamics, the universe is very specific. It's your system plus your surroundings. That's your universe. You're studying your system, and then your surroundings are everything that are not your system. And we refer to that as the universe. And so, for example, if you start thinking of endothermic reactions are heat energy flowing into the system. So the surroundings send heat into the system. Exothermic, heat energy goes from the system out to the surroundings. And so here you kind of see a mock-up of you have your little system there. Heat energy is coming from outside that system into the system, uh, and that's an endothermic reaction. The reason that happens is, for example, imagine you have a reaction that doesn't have the capability to run on its own. You mix chemicals together, they don't do anything. Well, for a lot of systems, you can pump energy into the system in terms of heat, and then all of a sudden a chemical reaction will occur because the heat is absorbed, and then the reaction occurs. An example of when you could feel an endothermic reaction, and I don't know, kind of like Hagrid, and shouldn't have told you that. Should not have told you that. But those, when you take organic chemistry, you have this compound called acetone. Some of you are already familiar with it if you use nail polish remover. But you notice if you ever get it on your hand, all of a sudden you feel very, very cold, and that acetone evaporates very fast. Well, that's because the acetone sucks up a ton of heat from your hand, evaporates very quickly into gas. It's a volatile substance, and it leaves your hand feeling cold from the heat that was pulled away. Another example, and again, you don't want to do this. You don't want to do it in lab. You don't want to do it anytime. Uh, but when you mix together, say, water and concentrated sulfuric acid, uh, your beaker is going to get very, very warm. Well, that's because that's an exothermic reaction. So the actual mixing of the water and the sulfuric acid puts out a lot of heat. And so you can think of this in terms of potential energy as well. I mean, like your sulfuric acid and water, uh, the uh, the reactants have very high potential energy, and that's why when they mix, they put out heat. They're putting out a lot of they have a lot of energy to put out. And so you think of that like your ball on top of the hill. You don't need to do much. It's ready to just roll down that hill. And so you can think of that. You think of the water and the sulfuric acid is what state do these want to be in? Well, your sulfuric acid is strong. Remember, we talked about full dissociation. Your sulfuric acid in water, they really want to be in ionic form. So they're going to go quickly from just water and sulfuric acid into ionic form. They're going to go rolling way downhill. And since they really want to be in ionic form, they're going to put out tons of heat as energy as they become more stable versus a reaction that's endothermic, where your reactions have very low potential energy. So they need energy. Again, think of your ball and your object in a gravitational system. Energy is needed to move that object up to a higher level. So energy has to be put in order to go uphill. And so that's the idea of an endothermic reaction. Energy is taken for the reaction to then proceed to the products. So a couple ways we can look at this. Um, Thermodynamics has a sign function. So exothermic, uh, in an exothermic reaction, energy flows in the form of heat from the system into the surroundings. So heat escapes the system. And we view everything from the viewpoint of the system. So when heat escapes, you're going to get a negative value. So your system is losing heat. And what you'll see a lot of times is this negative delta H or negative enthalpy. And so heat is escaping your reaction. That's an exothermic. A good example, and the way we write our chemical reactions, is here your hydrochloric acid mixing with sodium hydroxide. You're going to get your salt, you're going to get your water, and you're going to get a lot of heat. And so in an exothermic reaction, heat is going to be a product of the system. And the opposite for an endothermic reaction, heat energy has to be put in, heat energy has to flow into the endothermic reaction. And so since the system is getting energy, you have a positive number. So a positive value for your heat energy or your positive delta H. A good one here is your photosynthesis reaction, where heat is a reactant. Heat is needed in order to make the reaction go. So you have your carbon dioxide plus water plus the heat put in from light, and then you're going to get your C6H12O6 plus your oxygen as your products. So this here is a sugar. It's the exact same chemical formula for glucose and fructose. Predominantly, photosynthesis produces glucose. That's not to say it'll do that every time, but predominantly you're going to get glucose out of your photosynthesis reaction. And if you want to know the difference, just look up the structures of glucose and fructose. You'll see glucose is a six-membered ring, fructose is a five-membered ring. And so that's what thermodynamics is. It's the study of energy and its interconversions. So we need to start learning the laws of thermodynamics. This first law of thermodynamics is really the expression of the conservation of energy in thermodynamic terms. Uh, Always remember the energy of the universe is constant. You have energy flow between system and surroundings, but the total energy of the universe is constant. Let's say energy is flowing out of the system, whatever the negative of the system is, and the positive of the surrounding is, when you add them together, it has to equal the total energy of the universe. So here, your book uses delta E. A lot of other books use delta U, so same thing, equals Q plus W. That's your first law of thermodynamics. So this is internal energy of your system equals heat plus work. A few more mock-ups of exothermic and endothermic reactions to help you get more of a beat on what those are, but we're going to work with this first law of thermodynamics. Now, delta U, internal energy, is a state function. Does not matter how you get from beginning to end, just as long as you have a value at the beginning and the end. Q and W are not state functions. Remember, work depends on how the path you take. Heat depends on the path you take. So how can adding these two together give you a function that doesn't care about path? Well, it's because the way heat and work balance out the energy exchange, uh, it really cancels the energy exchange and heat and work coming together cancel out the need to know the pathway. We could go into a big long derivation, just know that heat and work together really cancel out the need to know that pathway, and you end up with a state function, delta U. So again, we kind of look at this. I wanted to put in this sign convention. So remember, negative sign is something leaving the system, positive sign is something coming into the system. Again, think of this as you're thinking about exothermic and endothermic reactions. But let's start by solving a simple exercise. Let's calculate the internal energy of a system where the system expels 47 kilojoules of heat while 88 kilojoules of work is done. What does the positive work done mean? Okay, so we have to start looking at our numbers here. So we're being asked, what is delta U? Well, the system expels 47 kilojoules of heat energy. Expels. That means the heat's leaving the system. So that means Q is a negative 47 kilojoules. And then it tells you work is a positive 88 kilojoules. Wow. Positive 88 kilojoules. So our theorem is the first law of thermodynamics, E plus W, which in this case is negative 47 kilojoules plus 88 kilojoules. And you're going to end up with 41 kilojoules as your internal energy, or the change in your internal energy. Now, positive work being done. This is again something else, and we'll just keep covering these kinds of ideas until they start to sink in. But positive work, remember, everything is uh, viewed from the standpoint of the system. So positive work the surroundings do work on the system. So we're going to use this example here in a second, but you can think of this as a piston. When the pressure outside the piston compresses the piston to shrink the volume inside, that's positive work. So the surroundings did work on the system. It would be negative work if the piston, the pressure inside pushed back and expanded the volume and pressed against the external pressure. So here's our piston. So we have a piston of surface area A, and we're looking at an expansion. You're going to get, we're really trying to figure out this new expression for work, negative P external delta V. Okay, so let's get our piston here. That is not what I drew. Really want this to look like it's on its side. Yeah, good enough. Okay, so we're going to imagine that this is our piston. It had been moved. So initially, it was here, and now it's here. H initial, H final. Moves through delta H. So you can think of it as an expansion. Well, it has a surface area A outside. There's pressure outside. There's pressure inside. I can move this up here. Okay. Then we have to think about, so when you take physics with me, you're going to work on what's called free body diagrams. Usually I put that at the center, but the A's there. So there's two forces really acting here. There's a force moving the piston up. There's a force of gravity, which equals mass times the gravitational acceleration constant, g, pulling the piston back down. Okay, now, the way we start analyzing this is we say, well, we want to think of this in terms, so let's think of it without the piston moving, okay? And this will make sense once we get towards the end. So when the piston isn't moving, the force pushing up on the piston and the gravitational force pulling down equal each other. And so if we say, well, the sum of all our forces, and then of course, you always want to pick positive and negative directions. So down is our negative y direction, so negative. So the sum of our forces is going to be the force pushing the piston up plus force of gravity equals 0. That's going to be, so then that we just know that as F. Force of gravity is minus mg because you see which way, you see that force of gravity is pointing down, 0. So our force has to equal the magnitude of our force of gravity. Okay, so remember we said work is F dot D, so a dot product. This is very simply put F times your distance times the cosine of theta between the two vectors. And so you see that your F is that way. Your distance is that way. And so that you see between these two, theta equals zero. There's no angle. They both go in the exact same direction. So this is F times D. Cosine of zero. Cosine of zero is a 1. You can put that into your calculator. So our work is our fourth times our distance. Now, what is our distance? This is F times delta H. And then what did we say F was? So this is going to be mass times gravity times delta H, which oddly enough is the exact same formula for potential energy. Now, we're going to pull this little trick we always pull in physics called multiply by 1, because I remember pressure is force over area. Okay, so what I'm going to do is now work is going to equal area over area, which equals 1, mg delta H. And we're going to break this up like this. This is going to be mg over A times A delta H. Well, if you notice, mg over A is force over area. So that means this is going to be pressure. And then the surface area times delta times the length, that is the volume of a cylinder. And so this is area, as it says it's A delta H, this is change in volume, P delta V. Now, we said that it's negative P external delta V. Now, the reason we think of this in terms of the system being in equilibrium, or the force up equaling the force down, is when we study these systems thermodynamically, we don't want, for example, our piston accelerating wildly. We want to be able to measure what's going on. So, uh, what we say is that for the piston to move up, we want the internal pressure moving the piston to be infinitesimally smaller than the external pressure. So they're almost equal. They're just off by a tiny, tiny, infinitely small little bit, so that the piston moves up very slowly. So they're essentially equal. And since the pressure inside is positive, and it essentially equals the pressure outside, the external pressure, what we end up with is work is negative P external delta V. And so that's work in this is how we look at work in terms of a gas. And so thinking of your sign conventions, when a gas expands against an external pressure delta V, by delta V is positive. So an expansion, delta V is positive, that makes work negative. Because when you expand, the uh, the system is doing work on the environment. So work is negative. Work energy is leaving the system, and vice versa. When the pressure external pressure uh, decreases the volume, work is being done on the system. So work energy is being put into the system. So work is positive. Okay. I feel like we're getting a good start on thermodynamics, because I feel like this is all we're already going to be sitting there at least on one topic going, what the heck? That's good. That's the goal of thermodynamics, is to make you want to slam your head in a door. But we're going to keep going. So a piston performs work of 210 liters times atmospheres, which is another way you could, there's a conversion from that to joules. We won't need it this time, but we will need it on the next one. Uh, Work of 210 liters times atmospheres on the surroundings, when the cylinder in which it is placed expands from 10 liters to 25 liters. At the same time, 45 joules of heat is transferred from the surroundings to the system. Against what pressure was the piston working? What's the external pressure? Let's see. So, work done on the surroundings. So, work is negative 210 liter atmospheres. Your initial volume, 10 liters. Final volume is 25 liters. And then heat is expelled. So these are quantities that I know. It just so happens that, and this is something you want to make sure you're practicing at. We don't actually need the number for heat. Doesn't help us solve the problem. Just study things like that because especially standardized exams are going to give you information and a problem you don't need. So let's see if we can figure this out. So work, our theorem is negative P external pressure, delta V. Okay, we're going to change this around. Work divided by delta V. And then we want to make this side positive, negative work V. Okay, so now we can plug in numbers. Let's see, this is negative. Negative 210 liter atmospheres over 25 liters minus 10 liters. And always and remember, your deltas are final minus initial. And so your the external pressure that you're moving against is 14 atmospheres. So if you can't tell, this is high pressure because atmospheric pressure at sea level is 1 atmosphere. So 14 atmospheres would be deep underwater. All right, let's look at another problem. Here's a more chemistry-based one. 1 mole of water vapor at 1 atmosphere and 100 degrees Celsius occupies a volume of 30.6 liters. When 1 mole of water vapor is condensed to 1 mole of liquid water at 1 atmosphere and 100 degrees Celsius, 40.66 kilojoules of heat is released. So an exothermic reaction. If the density of liquid water at this temperature and pressure is 0.996 grams per cubic centimeter, calculate the internal energy for the condensation, the delta E or delta U, change in internal energy for the condensation of 1 mole of water at 1 atmosphere and 100 degrees Celsius. Okay. Okay, so here's a conversion that you're going to want to know. 1 liter atmosphere equals 101.325 joules. What? Water, 18.02 grams per mole. The density of liquid water is 0.996 grams per cubic centimeter, which also means it's 0.996 grams per milliliter. Remember, it's 1 milliliter per 1 cubic centimeter. Our final volume is going to be the volume of the liquid. Our initial volume is the volume of our gas, which equals 30.60 liters. Our external pressure is 1 atmosphere. So essentially the room you're sitting in now. And our heat exchange, so exothermic negative 40.66 kilojoule. Okay, so what is our theorem? Okay, so that's going to be delta U, Q plus W, but it's also going to be Q minus the external delta V. So we need all of these pieces. Let's work on delta V. V final minus V initial, which is going to be the volume of the liquid minus the volume of the gas. Okay, so we remember that density is mass over volume. When we move this around, the volume of the liquid is going to be the mass over the density. We don't have the mass of the water. What we do have is number of moles and a molar mass. So we remember that mass is number of moles multiplied by the molar mass divided by the density. So this is going to be 1 mole times the molar mass over 0.996 grams per milliliter. This is going to give you 18.09 milliliters or 0.0181 liters. Okay, so that means delta V is going to be 0.0181 liters minus, and then the volume of our gas is 30.6 liters. This is going to give us a negative 30.58 liters. Okay, so now let's look at our work. Okay, so thermal pressure delta V is 1 atmosphere times negative 30.58 liters. This is going to give us a negative 30.58 atmosphere liters. But we need this in kilojoules to match Q. So we need to do some conversions here. Negative 30.58 atmosphere liters. (101.325 joules per, well, liter atmosphere. Atmosphere liter doesn't matter. And then we know that there are 1,000 joules per kilojoule. And this is going to give us negative 3.10 kilojoules. Okay, so now delta U is going to be Q minus the external delta V That's going to be a negative 40.66 kilojoules minus a negative 3.10 joules. And so our change in internal energy is negative 37.56 kilojoules. So that's our internal energy for our system. Okay. Well, we're going to pick this back up on Monday, and we'll just keep plowing through thermodynamics. Until then.